3 days after a magnitude 7.3 rupture tore open the Middle America Trench near the border of Mexico and Guatemala, the physical mechanics of crustal relaxation encountered a severe structural anomaly. Standard geophysical models mandate that post-seismic rupture energy decays predictably over time, along a logarithmic decay curve. For the first 24 hours following Friday's main shock, the subduction zone off the coast of Chiapas appeared to obey these classical boundary conditions. A magnitude 6.0 secondary event arrived approximately 30 minutes after the primary slip, matching the statistical upper limit expected for a rupture of that scale. Subsequent stress releases through Friday night, including a magnitude 5.2 event shortly past midnight, led observational monitoring networks to classify the sequence as a routine release of accumulated strain. Then, the systemic decay collapsed. Over a 9-hour window spanning Saturday evening into early Sunday morning, the targeted offshore rupture zone experienced a sudden, highly concentrated cluster of activity. At least 8 distinct earthquakes, exceeding magnitude 4.5, materialized within a narrow spatial corridor roughly 90 kilometers across. 3 of these events crossed the magnitude 5.3 threshold, culminating in a magnitude 5.7 earthquake 72 kilometers southwest of Puerto Madero. This maximum burst event did not arrive during the initial phase of maximum instability. It struck a full 24 hours after monitoring agencies had formally assessed the sequence as fading into background seismicity. The spatial distribution of these events further defied standard post-rupture geometry. 3-dimensional seismic mapping revealed a flattened, spreading footprint measuring 32 kilometers from north to south and 83 kilometers from east to west, a spatial smear of epicenters where classical friction models predict a tightly concentrated structural cluster. To evaluate the true scale of this anomaly, one must examine the broader planetary baseline. During the exact time frame of this offshore burst, the global catalog of earthquakes at or above magnitude 4.5 rose from 137 to 144 events over a 7-day tracking window, across 40,000 kilometers of active global plate boundaries, spanning the entirety of the Pacific Ring of Fire, the Mid-Atlantic Ridge, and subduction zones from Kamchatka to Chile. Virtually the entire net statistical increase in moderate planetary seismicity was generated by a single 90-kilometer box of seafloor off the southern coast of Mexico. This hyperconcentration of energy release occurred along a subduction interface, where the Cocos plate descends beneath the North American plate at a rate of 76 to 88 millimeters per year. Yet, as analytical models attempted to map the structural architecture of this burst, primary observational instruments ceased to agree. It is within this shallow, locked geometry that pre-failure slip cascades and foreshock sequences manifest. Conversely, if the hypocenters sit at depths of 29 to 35 kilometers, the activity represents intraslab deformation, where the descending Cocos plate fractures under its own gravitational weight. Intraslab ruptures, while capable of generating substantial regional shaking, operate on distinct stress regimes and rarely act as immediate triggers for megathrust slip. Because automated, non-reviewed records dominate the initial catalog feeds, the observational data currently fails to distinguish between a routine intraslab stress release and an active megathrust foreshock sequence. In retro-analysis, foreshocks and ordinary aftershocks are physically indistinguishable during their evolution. Geodynamic data confirms that approximately 5 to 10% of moderate earthquakes are retroactively classified as foreshocks when followed within days by a larger rupture. Concurrently, a significant percentage of major subduction events exhibit prior low-magnitude clustering. The structural parallel is exemplified by the magnitude 9.0 Tohoku earthquake off Japan in 2011, which was preceded 2 days prior by a magnitude 7.3 event. At the time of its occurrence, that magnitude 7.3 event displayed the statistical signature of a main shock with a standard aftershock sequence, demonstrating that real-time instrumentation cannot deterministically separate a decaying strain release from a precursor sequence. As the Chiapas cluster evolved, secondary seismic activity manifested along neighboring plate boundaries, prompting claims of wide-scale regional stress synchronization. Moderate events emerged along the North American Caribbean plate boundary, including a magnitude 5.1 earthquake south of Grand Cayman and magnitude 4.7 events off the Pacific coast of Nicaragua. Evaluating these distant events against the physical laws of stress transfer reveals strict spatial limits. Static stress transfer, caused by permanent crustal displacement along a fault, alters failure thresholds only within 1 to 2 rupture lengths of the primary slip. For a magnitude 7.3 event with an 80-kilometer rupture zone, static loading is physically bounded within a radius of 100 to 200 kilometers. Grand Cayman, located 2,000 kilometers away along the Motagua-Polochic fault system and the Cayman Trough Transform, sits far beyond the reach of static stress loading. Long-range interactions can occur via dynamic triggering, where transient seismic waves pass through distant crustal structures. However, dynamic waves impart minimal energy and can only induce failure on faults already sitting at critical stress thresholds. While the Nicaragua events at 700 kilometers lie within the plausible range of weak dynamic triggering along the same subduction system, the Grand Cayman event represents a statistical coincidence on a distinct transform boundary moving at 20 millimeters per year. Similarly, claims that the Chiapas sequence can load fault systems in California are invalidated by energy attenuation. Static stress changes at a distance of 2,500 kilometers are effectively zero, leaving the extreme strain accumulation along the southern San Andreas and San Jacinto fault systems entirely independent of Mexican subduction dynamics. While long-range stress transfer to distant fault systems remains physically unsupportable, the localized structural reality of the southern Mexico subduction zone operates under extreme mechanical loads. Historical baseline records establish that the Middle America Trench near Chiapas is fully capable of generating destructive megathrust events exceeding magnitude 8. Since 1950, 7 distinct earthquakes of magnitude 7.0 or greater have ruptured within 155 miles of this specific offshore corridor. The region's catastrophic potential was explicitly demonstrated in September 2017, when a magnitude 8.2 intraslab normal faulting event tore through the Tehuantepec region at a depth of 70 kilometers, resulting in approximately 98 fatalities. That 2017 rupture proved that the subduction complex can sustain massive structural failure, though its physical mechanism, the descending slab tearing under its own weight, differed fundamentally from a locked interface thrust. To establish whether the ongoing Chiapas sequence represents a transient post-rupture adjustment or the precursor to a larger megathrust failure, seismologists rely on a single, falsifiable empirical threshold. According to observational criteria established following the initial magnitude 7.3 rupture, the classification of this sequence as a normal aftershock decay holds only so long as the activity remains below a specific magnitude boundary. The definitive marker for an elevated failure trajectory is the appearance of multiple secondary earthquakes reaching or exceeding magnitude 6.0. As of the latest catalog measurements, that critical physical threshold has not been breached. The initial magnitude 7.3 main shock produced a magnitude 6.0 secondary event 30 minutes later, matching statistical predictions for maximum aftershock size, but no subsequent event in the weekend burst has reached the magnitude 6.0 level. The maximum magnitude recorded during the elevated cluster remains capped at 5.7. Because magnitude scales are logarithmic, a magnitude 6.0 event releases significantly more energy than the 5.3 and 5.7 events recorded off Puerto Madero, marking a distinct physical regime in strain release. Misinterpretations surrounding this sequence have been exacerbated by catalog processing artifacts. Automated reporting feeds published short-term lists that omitted the magnitude 7.3 main shock while displaying truncated entry counts, leading to superficial claims that data was being suppressed. Similarly, an orphaned automated tsunami entry carrying an empty summary field persisted in public data streams long after local sea level stations confirmed only a minimal half-foot water level adjustment, standing down all coastal threat protocols. These discrepancies reflect database latency and automated system defaults rather than concealed geodynamic hazards. The current systemic status of the Middle America Trench thus rests on 3 verifiable metrics currently awaiting human analytical review. First, the magnitude 6.0 ceiling remains unbroken. Crossing this threshold would instantly invalidate the standard aftershock model. Second, human seismologists are re-evaluating raw waveform data to resolve the telemetry corrupted hypocentral depths, which will conclusively place the sequence either within the shallow locked megathrust interface or deep inside the bending slab. Third, monitoring networks are tracking whether secondary seismicity along the Caribbean-North American plate boundary, including the Motagua Fault and Swan Islands transform, remains isolated or develops into a sustained regional cluster. Until these reviewed datasets are finalized, the Chiapas anomaly remains a high-rate, spatially expanded strain release on a major subduction trench, demonstrating the strict observational limits of real-time geodynamic analysis. The ultimate significance of the Chiapas offshore sequence does not lie in sensational claims of global plate collapse, but in what it exposes about the rigorous boundary limits of modern geophysical measurement. The human instinct to connect distant geological events into a single unified narrative of impending catastrophe is consistently refuted by the physics of crustal mechanics. The wave energy and static stress changes generated by a magnitude 7.3 rupture decay far too rapidly with distance to load fault structures thousands of kilometers away. California's seismic risks, including the extreme strain accumulation along the southern San Andreas and San Jacinto faults after 169 years of quiescence, remain entirely localized processes governed by internal plate boundary dynamics, unaffected by events off southern Mexico. What the empirical data actually reveals is a subduction system operating under immense mechanical loads, generating a post-rupture stress field that behaves at the extreme edge of statistical models. The persistent failure of the Chiapas cluster to decay according to standard power law curves demonstrates that energy release along active plate boundaries is frequently nonlinear and spatially complex. Rather than smoothly dissipating strain across a single rupture plane, the Middle America Trench is accommodating post-seismic slip through distributed faulting, potentially activating adjacent lock patches or intraslab fractures across a broad spatial footprint. The resolution of this geodynamic ambiguity depends entirely on incoming data streams that will systematically replace automated approximations with human-reviewed physics. The critical empirical indicators remain clear and publicly verifiable: whether subsequent energy releases breach the magnitude 6.0 threshold, whether relocated hypocenters converge onto the locked megathrust interface or deep within the descending Cocos slab, and whether secondary activity along adjacent plate boundaries subsides as baseline statistical noise. Until those reviewed solutions are published, scientific pragmatism dictates accepting the data as it exists, a highly active, depth-ambiguous, and spatially expanded aftershock sequence, occurring along a trench capable of generating catastrophic megathrust ruptures. The instruments have documented an anomaly that defies simple categorization, demonstrating that even in an era of global seismic networks, the deep architecture of subduction zones retains structural complexities that push our analytical models to their absolute limits. The Earth has not broken its physical laws, it has simply revealed the boundaries of our ability to observe them in real time. In the final analysis, the event off the coast of Chiapas serves as a stark case study in the structural limits of real-time geodynamic monitoring and short-term seismic assessment. The fundamental contradiction that emerged over those 9 hours on Saturday evening, a sequence classified as decaying according to classical, Amori-type statistical laws that suddenly accelerated into a localized burst of moderate earthquakes, exposes the true operational boundary of modern observational science. The sequence did not obey the neat, linear trajectory expected of it, not because the underlying physical laws failed, but because subduction zones are nonlinear, highly heterogeneous physical systems operating under massive mechanical stresses. Every diagnostic tool deployed across this sequence carries a known structural limitation. Automated depth solutions, constrained by single-sided array geometries along the coastline, defaulted to 10-kilometer placeholders, obscuring whether slip was occurring along the shallow, locked megathrust interface or within the deeper, bending core of the descending Cocos plate. Public reporting feeds, subjected to truncation artifacts and database latencies, temporarily dropped the primary magnitude 7.3 event and preserved orphan tsunami records, creating artificial analytical gaps. These operational realities demonstrate that raw catalog data, when stripped of human review and contextual physics, easily gives rise to spurious interpretations and ungrounded claims of global plate synchronization. When evaluated purely through the lens of physics and stress transfer budgets, the scope of the crisis contracts to its true, localized proportions. The idea that this offshore Mexican rupture could mechanically load fault systems thousands of kilometers away, whether along the Motagua system, the Cayman Trough, or the high-stress segments of the southern San Andreas, is disproven by the rapid spatial attenuation of static stress and the negligible energy imparted by dynamic triggering. The true critical threshold remains strictly local, encapsulated by a single, falsifiable empirical test, whether secondary ruptures cross the magnitude 6.0 threshold. As long as the sequence remains capped below magnitude 6.0, the most plausible reading remains that of a highly productive, spatially expanded, but non-catastrophic aftershock sequence along a major subduction trench. Yet, because the largest event of the cluster arrived a full day after the system was pronounced normal, and because hypocentral depths remain scattered across a 25-kilometer vertical swath, the possibility of multi-structure activation on a trench capable of generating magnitude 8+ megathrust ruptures cannot be ruled out by current instrumentation. This is the sober, unvarnished reality of geophysical analysis. Science cannot offer short-term earthquake predictions, nor can it instantaneously resolve deep crustal mechanics from offshore stations. What it provides instead is a framework of hard limits, energy budgets, and precise measurements. The Middle America Trench has demonstrated its capacity for complex strain release, leaving a clear diagnostic signature recorded in the instruments. As human seismologists complete their reviewed waveform solutions, the true physical architecture of this sequence will be formally established, reaffirming that nature operates not according to human expectations or simplified models, but according to the strict, uncompromising logic of structural stress and physical limits.